Okay, measuring temperatures. This is what I wanted to start this lecture with in more detail. And we already discussed about a number of different options, including suggestions to point cameras at mercury thermometers and all other kinds of practical ways of measuring temperature. And we already said that this is a classical effect, which you all know from physics, right? Why are you laughing now? Based on the distribution of temperature over metal and the automatic result of voltage differences based on that, which also goes back to thermal noise in the metal itself. And as this is only measuring noise temperature between two ends of a piece of metal, which is not particularly useful to measure temperature, usually combine this, as we already said last time, in a structure like this, and this is what is called a thermocouple. The trick here is that the material of the two wires in this thermocouple has to be different so that the temperature, the voltage differences over these two wires is different, even though the temperatures on both sides are the same. Which means it translates into there will be a voltage difference at the open end of this thermocouple. And as you already observed, this is only measuring differences between temperature. So you get the temperature difference to what is called your clamp temperature, namely there the point where the two wires come together. This is your reference temperature, and you measure the temperature from there to the point which is exposed to the outside. Those cables can be relatively long, but there are lots of different things to be decided upon. Okay, so far you're convinced. You saw thermocouples in the lecture. Go in the shop, say I want to have a thermocouple. A few questions. So the first question may be, how do you want to mount this? Do you want to have this just wires hanging out at the end of this device? Do you want those wires be connected to some casing so that you measure the temperature ultimately of your casing, conducting the temperature to your tipping point of your thermocouple? Do you want to have it ungrounded? It means you have it inside a casing, which gives you the possibility to protect your thermocouple from whatever you dunk it into. Because often you want to measure temperatures in quite unpleasant places, right? Where you do not want to have your metal directly exposed, because it could require reoxidizing straight away, or melting, or burning. Right? None of these things are particularly useful for thermometers if they're just starting to burst in flames straight away. So you have to be concerned about how to do that cleverly. After you pick some form of mounting casing for the tip of your thermocouple, the next question is, of course, okay, you have two different pieces of metal. Now, there are lots of different metals. Which of the two do you want? Classical combinations are those four here, but we see a few more in a second. Copper constantan, ferroconstantan, nickel chromium. And quite a few of them are also based on platinum, or at least some percentage of platinum. As you probably remember, platinum is not the cheapest piece of metal you can buy. And just buying a spool of platinum wire is probably not what you have in your hobby shop at home. And having long wires of that kind of metal is very useful for measuring specific forms of temperature, but it could become very costly quite quickly. This gives you a bit of an idea about how the voltage of those thermocouples relate to the temperatures you expose them to, or the temperature differences you expose them to. They're surprisingly linear, not perfectly, so you still have to, particularly at higher temperatures, you definitely have to compensate for the nonlinearities and have to model for the nonlinearities there. They're reasonably linear over quite a large range. And you can expose them to temperatures where you don't want to have your fingers usually, which is somewhere north of 1,000 degrees Celsius. And if you use some of these W pairs, then you go beyond 2,000 degrees Celsius here.
Looks like it's got a very low gradient. So if you want to change like a temperature of 1 or 2, you might have only a millivolt difference.
Yes.
Is that easily and accurately measurable?
Hundredths of a millivolt. Okay. Is that going to be an issue? Is that going to be a problem?
Yes.
Yes. No. Mm-hmm. Yeah. Well, one of the first questions which I would ask, do you get this voltage difference even to your amplifier?
Yeah.
Or is your cable so long that by the time you actually connect this up to your amplifier, this thing is all evaporated as radio waves somewhere else, and you actually don't measure anything there?
For the lower ones, like that was an estimation from the top one, but the lower one really works.
Well, the lower ones you would particularly employ for very high temperatures, obviously, for a number of reasons. First of all, they're a little on the expensive side, and you don't want to have them to measure room temperature. You don't dish out that kind of money for that to start with. Plus, they're not very sensitive at room temperature to start with. They don't do much at room temperature. So you're not measuring over this whole range. You have usually only a very narrow thermal band. If you want to, for example, measure the temperature of some melting metal someplace, you already quite safely assume it's above room temperature. You don't measure for the whole range here. Right? But of course, it will come back, and we will discuss this in much more detail. How much can you resolve here on these voltages? What will be the noise in the whole process to getting those voltages into your computer? Actually, we'll probably talk about this by the end of today's lecture. Okay. Yeah.
Just a few lines there. Is there other materials you know that have a much steeper gradient, or you just use a different method for the low temperature, the low range higher specific?
Yeah, I wouldn't actually know whether there's any combination which has a steeper gradient. Possibly. This is a mixture of what you can possibly buy, of how the materials deteriorate in practical environments. So this is highly practical driven. This is not physics driven in that sense. You could probably define other thermocouples from a physical point of view, which have other characteristics but are not used in practice for other reasons. I will show you in a second what other considerations you have there. If you read, for example, what you can do with a specific thermocouple, it's not just the temperature range. It is also, for example, to what degree they would survive in specific environments. The N-type, for example, in oxidizing, inert, or dry inducing atmospheres. J-type suitable for used in vacuum, reducing or inert atmospheres. Ultimately, what you have there is this is not polished, shining metal. This is just plain, pure, exposed pieces of metal, and most of these have a tendency to rust. And you often want to have them in environments like the outdoors, your melting pot of your pieces of chemical, which are even more aggressive than your office environment for these metals, so you have to be very careful. And sometimes they're also employed under the premise that this thermocouple will survive in my machine for about a week. Then it's just gone, it's dissolved, it's no longer there. I have to replace it. But I don't have much of a choice because the temperature range in my environment is like that. And I cannot have the luxury of fully producing some kind of a vacuum in there. So I have to buy into that one. And if you have to measure temperatures in a big pot of some chemicals, things often get even worse because they can be highly aggressive to anything you put close to that anyway. You want to then put a thermometer into that. And this goes on with up to the tungsten rhenium alloy versions, which are the extreme high temperature versions. And these extreme high temperature versions are inherently disastrous for quick oxidization. They are rusting away extremely quickly, which is not great because you don't have much choice in those temperatures above 2000 degrees. You don't have many metals which you can still use there. Most of your other combinations have simply already been melting away, or at least losing their characteristics at those kind of temperatures already. So thermocouples, nice. What can you do with them? Small, can be relatively cheap, at least for the lower temperatures. Require a highly stable amplifier, which refers to the question of you only have a very small effect which you measure there, so it has to be a very fine and stable amplifier on the other hand. And you cannot just extend those cables randomly. So if you want to extend those cables, you need to actually use the same material for the cables themselves as well. Okay, that's the thermocouple approach. Let's go through a number of other possibilities. Thermoresistors, which is simply using a piece of metal, and this is usually platinum, spread out extremely thin, which has a very well-defined and somewhat linear characteristic with resistance characteristic with respect to temperature. All straightforward enough. You just have a relation between temperature and the resistance of this piece of metal. Then you have a defined length of that, which you unspool on some ceramics or other carrier material which you want to use for that. And you're done. Usually on glass or ceramics. They're reasonably cheap. But a number of things which we have to consider here. Thermoresistors, you have to model their linearity a little bit more carefully, not quite as linear. This is the characteristic for the classical PT100. Calibrate this thing carefully, and you also have to be taking into consideration that your sampling frequency will be very low by the very definition of that. This goes for lots of thermometer technology. That kind of understandable why? Why you cannot measure at infinitely high frequencies? It's just a question of energy transfer. You need to actually get the temperature someplace. You need to heat it up. You need to heat up your element. You need to heat up your sensor element. It has to actually get to the same kind of temperature. And this energy transfer always takes time and energy. So you also take energy out of the system simply by measuring it. Oh.
Can you not just leave it in there? So it all equalizes?
Yes, but you're still changing the overall thermal resistance of your system if you have all of a sudden more metal in it, for example. Right? So you always change the characteristic of any system if you put more material or more devices into it. And in the case of the thermometer, you usually want to actually be in physical contact. You always have to be in physical contact to measure temperature? No? Can you measure temperature on a distance? Can you measure my body temperature from over there? Infrared. Or black body radiation sensing. Most of these small handheld thermometers which are going over some distance are doing that. Very handy if you want to measure temperature on stuff which burns your fingers and you don't want to touch it with anything easily. So red body radiation, black body radiation is another possibility. Let's stick with the thermoresistors for a moment. There's another effect of that. How do you measure resistance? Practically, how do you do that? Yes. Yes. So you put it in the voltage divider. You see what voltage you get over this resistor. What does this mean for the energy distribution in your whole system? You're adding energy because you put some voltage through that onto that thing, which means you put some current through it. You put some current through your thermometer. What will your thermometer do if you put some current through it? Okay, so that's a bit of a self-fulfilling thermometer. You just put enough current through it and it will be warm eventually. How much current can you put through that? Simple calculation for the PT100. If you want to measure, say, in the ballpark of half a degree in terms of precision, so to turn this upside down, you can only apply enough voltage to it so that it maximally can heat up a half a degree by itself in the process. And you use the thermal resistance of the casing in which you bought this thing in. And the thermal resistance is defined by the temperature difference divided by the power, the electrical power you put through that whole thing. And then you can just resolve those equations and go back to the maximum voltage you can possibly apply to that one, which is interesting. So even at a third of a volt, your PT100 will already heat up a half a degree. So you have to be quite cautious about that. So putting this thing to 5 volts is probably not what you want to do that there. If you put the voltage further down, you will heat it up less, but you will of course increase also the noise in your measurement, because then your voltages become smaller and smaller, your currents become smaller and smaller, and your whole system becomes more fragile to any kind of noise and measurement errors in the process.
Like it's still 1,000 times larger than the differences in the
Yes, but it's a bit trickier to measure. The other one is it's basically a very similar and related problem, and you're right in that sense. You still have to be careful that you're talking usually about 10, 20, 100 millivolts maybe, which will be practically used for that kind of environment, which is different from what you're used to working in your electric circuitry if you want to measure a substantial signal which is easy to measure. Further optimization. You add additional wires which will enhance the position of the whole operation. You add a reference resistor, which is also a PT100 in a controlled temperature, so that you can compensate for some linearities by having multiple of them in different temperature zones. That's a classical way of doing that on top. So it's not quite as trivial as just measuring the voltage drop over your resistor. You have to be a bit more careful and subtle in the design of your setup here. What do you get out of that? One big advantage of resistance measurement is that you actually measure absolute temperatures as opposed to relative temperatures with thermocouples, which is often a big difference in practical application. They are a little less robust than thermocouples. Thermocouples are just a bonded pair of wires. So this is mechanically reasonably robust, while these resistors are often potted on ceramics or glass, and they're just mechanically a bit more fragile. And if you have a hair crack somewhere in the thermal resistor, then of course the whole effect is gone as well. So they're a little bit more fragile. If you have a highly turbulent environment, a highly mechanical vibrating environment, this can be a consideration as well. So how do you measure temperature in your CPU? You all have displays on your screen which tell you the temperature of your CPU in many different spots by now. How does that work? Is there a thermoresistor in your CPU? Would that be reasonable? have a thermal resistor in your CPU?
Thermal transistors?
Thermal resistors would be probably considered a complete waste of space because they would be way too large with respect to your whole system. So you have your thermal resistor and you have your CPU, and I don't know, that can be a bit clunky. I'm overdoing it a bit, but with respect to the resolution, what you see on a CPU is gigantic. You would have here. Say again? Can you have a what?
Thermal transistor.
Thermal transistor. What is a thermal transistor?
It's like transistors. So if we've got lots of temperatures.
Yeah, you're actually on the right path. Because I said last time, pretty much anything you do will be influenced by temperature. So often you actually start from what you already have. What do you have on a CPU?
Tons of transistors.
Lots of silicon, lots of transistors, lots of semiconductors. Right? Now, does temperature have an effect on semiconductors? Sure it does. Right? Will that be perfectly linear? No. Do you care? Oh, no, not really. So the position of these temperature readings which you get from your CPU are... Say again? Let's have a look at the actual curves, what you have. You have negative temperature coefficient effects and positive temperature coefficient effects. And are they nonlinear? Heck yeah. So you have to compensate for that quite nicely. But fortunately, they work reasonably well. They give you some resolution around the range which you are most interested in, namely something like 50 to 100 to 120 degrees. Once your CPU gets beyond 170 degrees, you begin to start worrying anyway. Once it goes beyond 200 degrees, you probably need a new one anyway. So you're not that fast about those extreme angles here. And unfortunately, there is a whole range for the positivities, for the PDCs at least, where your resolution will become a bit questionable because the response is so spontaneous and so steep all of a sudden that it's hard to resolve anything sensible in there. But the point is you get them for free. Just use basically the semiconductors which are already on your CPU, and you just optimize for the effect to make them extremely temperature sensitive as opposed to not so temperature sensitive, what you would do for the rest of your CPU, and you don't waste any further space on your CPU. It can be done quite compactly. So, super cheap, quite limited temperature range. I can squeeze some of them to 350 degrees, but that's about the end of it. And you have to definitely compensate for all the nonlinearities. So, if you are by now sick and tired of nonlinearities, I will recommend this one. You just use a device which directly measures the noise temperature of gas which is encapsulated in front of there. And this is actually directly affected by the movement of the molecules in this gas relative to the temperature which you expose that thing to, and you only need to know the Boltzmann constant for your gas which you use for that one, and the rest is, as you see in that equation here, perfectly linear. You just keep the frequency bandwidth constant and the rest constant, and the thing is directly proportional to your temperature. Cool, huh? Okay, there's a downside. This is probably one of the most expensive thermometers you can possibly buy, because that thing comes with quite a box of an amplifier behind it to actually measure these kind of effects in real life. And while this is beautifully linear over an impressively wide range, it's simply a very, very small effect which you measure here, which means you need to have extremely good amplifiers. I just noticed that I actually Americanized Boltzmann a little bit too much. I think Boltzmann was German enough that he deserves 2N at the end of the name, so apologize for that. And you measure from 1 to 2,500 Kelvin. Now that's what a computer scientist expects from a good sensor device. This is full range, border to border. You probably don't get much beyond that in any parts of this planet. So that's quite nice. Okay. Is that the end of temperature measurement? How many dozens of other forms can I just keep going here? Just measuring temperature. And it was not a no-brainer so far, right? I didn't sell you any sensor device so far where I say, oh, this is the one that beats it all. And you won't find that. You will always have to select a specific form of measuring for your specific environment. Just to mention a few more, which are classically used. Spreading resistors is a clever way of wiring lines of metal in a way that the density of these wires is changing over the base, which gives an interesting response to temperature. Crystals, piezos, which can be used for temperature measurements. And piezo crystals are wonderful. You can use them for so many things. What kind of usages come to mind if I say piezo for you?
Force sensing.
What sensing?
You can sense force with them.
You can sense force with them?
You can use them as speakers.
Yeah, you can use them as speakers. Yeah.
Yeah, I can say
Sound, yeah. So, what a universal piece of crystal. You can actually make music with it. You can, maybe you can cook coffee with it. It's fantastic. You can measure your weight on it. And this is all from pretty much the same kind of crystal. Wonderful. And you can measure temperature with it. Because the resonance frequency of your piezo crystal will be somewhat proportional to the temperature around it. You just have to change if you use the nice cut of your piezo that is maximally dependent to the outside temperature. Temperature controlled current source, that's another form of a semiconductor-based thermometer. It's quite cool. You can just buy this as an integrated circuit already. And it provides a constant current depending on the current temperature of this chip. Quite handy, easy to measure. Any kind of detecting changes in volume of metals and liquids of all sorts. Black body radiation, super handy thermometers. I always have one of them in the workshop, handy. And possibly many other forms which you can do for that. So, what did we learn so far? Probably that's not easy, I hope. And you will, unfortunately, not get around to read at least a part of the spec sheets for any sensor you're employing. So the take-home message is never assume that the thing which you buy is linear without any side effects, just measuring the effect just as a single effect and nothing else. And while this is not the only stage, we will talk about the actual conversion stage later in the lecture today, which has a lot of loss, linearities, noise, quantization associated with that. This is probably one of the more complicated stages to look into. Because without a basic understanding of physics, you will have trouble in that stage of your system design. Who feels confident about Physics 101 kind of interaction? That's a bit sad, actually. You will often find yourself in a position where just basic physics will come later on in your professional life, quite likely to the surface more often than you think. Simply for sanity checks, for things that, can this possibly be? Can this possibly fly? Right? And just simple physics considerations of how much energy do you have here, how much energy can you pump into that maximally, how much resistance do you have here, how can will that possibly have a chance to get off the ground in the first place? Basic physics understanding is quite essential if you want to be a part of a team which actually builds something. Okay. I thought that should be kind of normal for engineers, but you're not engineers. All of you are computer scientists. Any engineers? Oh, the engineers have to actually sit in front. Well, it's the engineering lecture theatre after all, so you have reserved seats, I guess. Okay. Well, I'm sure that the engineers at least feel comfortable about Physics 101. Right. So, how do you measure speed and range? We already discussed about a number of different possibilities last time. You just steal the speed camera of your local policeman in the village. That's one possibility to measure speed. Let's do it a bit more principled. Possibilities of measuring range, classically triangulation. What does that mean? Measuring range by triangulation? Yeah. You measure the angle in which you see something. So, for example, if you put yourself on the top of a building and you look down and you see a spot on the ground in front of you, you just can see, depending on the angle in which you see that spot on the ground, it must be in a different distance. And you can also see that if you do that kind of measurement, is that great for measuring something on the horizon? Probably a bit critical. Is it great for measuring something 50 meters in front of your building? Yeah, because then you have quite some variation in the angle in which you see something. If you see something on the horizon, the angle in which you see something is not varying very much. So you have, this is extremely nonlinear. It actually goes with the tangent of the distance, which is not exactly a linear function. Or any kind of time of flight measurement, which means you send energy out, take your stopwatch out, wait until some level of energy is hitting you back. If this is light, this is probably a pretty short operation, but other modalities, like, for example, sending out sound waves or pressure waves, can take easier time to be measured. Phase correlation, how could that work? Why is that a good idea? Using phase correlation for distance measurement? Phase of what? Phase of what would you measure? Yeah.
So if you send like a laser beam, then you measure the difference in phase between the signal you send out and the signal you're receiving.
Yeah.
And then you can get very accurate measurements.
Yeah.
Depending on the difference in phase.
Yeah. So that can be a lot more precise than your stopwatch approach. Because with your stopwatch approach, you have to wait until some amount of energy is coming in. Here you're actually on a much finer scale, because here you're actually looking at an individual wave of your signal, light in that case, and you can see how much will my signal be shifted from incoming to outgoing, and that phase shift gives you information how far that signal traveled. Now, unfortunately, if you travel more than one wavelength, you need to have other measures to find out that this is now all of a sudden a multiple of my displacement, so it doesn't universally work, but you can also combine that, and this is actually done. So you have systems which do take time of flight in the first instance to have some rough idea in what range I am, and then you take phase correlation on the second level to do the fine measurement inside each of the waves which is coming back. And phase measurement, You as experienced electronic engineers, of course, know that, how to do something like that. For the rest of us, I just give you that as a giveaway fact. Phase measurement can be done very easy and highly precisely with quite cheap electronics. So phase measurement, PLL circuitry, phase lock loop circuitry is something you can do in electronics quite easily. So it's cheap, highly precise to measure phases of signals. What else do we have? Intensity. Intensity is always a bit of a dodgy one. Right? This is, you switch on your torch, point it to something, and then you measure how bright the reflection is. That depends on a lot of things. And it also doesn't go very far because you need to be able to measure enough intensity back that you get some decent resolution out of that. It could be quite tricky to do that. Doppler methods. What can you measure with that? Yeah, relative speed. And you also do this acoustically and on the electromagnetic base to measure Doppler effects. We'll see actually an example for Doppler measurement in a second. So, measuring by triangulation, classical setup, cheap, at least nowadays. Whether you use a laser diode here or some infrared system doesn't really matter as long as it's focused enough. So you get a very narrow beam of visible or invisible light. But you have further safety restrictions. If it's invisible, then the total power which you can actually use here is reduced compared to visible light. So you can use higher power at visible light. Why? Because you can see it. But why is that allowing you to use higher power?
Step away when there's a big red dot showing on the ground next to you.
You particularly step away if you actually look into it, and you have a big red dot in your eye, and you immediately close your eye. So that gives you a chance of saving your eye. But if you have an infrared laser, and your eye is actually not detecting that, you will detect that your eye is dying based on the smell, because it just starts burning down, and before you know it, you have lost your eyesight without blinking, so to speak. And hence, if you go visible light, the safety regulations in most countries are a little bit higher power, because it's safe in the sense of you look into a visible light beam, you immediately will close down, it is safe enough, as opposed to invisible light, which is much more dangerous, because you can stare into invisible lasers for minutes without noticing, which is problematic. Anyway, what you do is you use a very cheap CCD line camera. So it's not a CCD camera what you have in your phone, it's a CCD line camera. Does that make sense? You just use one stripe of photosensitive cells, one row, instead of a whole array, a whole matrix. Easy. Because the only thing you're interested in is to measure the angular variation here. You don't want to take a picture of this whole thing. You only want to know where my dot has been going on this CCD line. Use some clever optics to increase the resolution a little bit in the process. And unfortunately, this whole effect goes with the tangent of the angle which you see there, which means that the further away your object is, the more noisy your measurement will become. So you use this usually for reasonably close-up measurements. But for that, it's quite easy. It has, unfortunately, another very problematic aspect to that, which is one of the aspects which made it illegal to be used in safety-critical environments involving humans because of that. If you measure by triangulation, that means you cannot, or it's hard to guarantee that you will always see this spot. It's easy to occlude that, because you will look at this spot from a different angle, then you illuminate that spot. You can easily construct a device which you illuminate with that one, where your laser is just going into a hole in there and you don't see it from another angle anymore, which is a bit problematic. So, other possibility, time of flight. And this is common today, time of flight measurements. If you go to, which is for me a bit fascinating historically, I can just go to the hardware store, and I've actually done that a few months ago, and got myself a new laser indoor measurement device, very nifty, very precise. And the fact that I nowadays can actually go into a hardware store and buy that, which is a time of flight plus face detecting quite high precision device, if you think about that one, for $150 or something like that, or for $100, is quite fascinating, considering that when I was sitting on your side of the lecture theaters, this was bleeding edge of research, for a simple reason that something like a gigahertz timer, which you need at the bare minimum to measure time of flight in a sensible way, was just about to become available. Silicon was not just clocked that fast back then, so we didn't have those kind of timers available. Nowadays, you get this in your pocket watch, and it's easy to buy this anywhere. Okay. Goodie. What can you achieve with that? Give you some practical examples. That's a 2D laser scanning device which we used or have been using in airborne systems. Here mounted on a rotating and tilting platform, so you can actually direct the measurement plane in direction you want. Can only measure up to about 30 meters outdoors. This whole thing is quite tiny. It's about that large in real life, so it's not a big device. It's small enough that you can easily mount this on airborne devices. This is here mounted on a 1.60 meter rotor span helicopter, so a fairly beefy device, which barely notices that kind of additional weight being put on it. Accuracy about 5 centimeters, depending on the range and the background light on that one, and 210 grams. That's quite nice for a little laser device like that. Also something which was quite out of the question just a few years back. Yeah. Why only 30 meters? What do you think? Why only 30 meters?
Because you have to measure the return signal. The laser is not powerful enough, it's going to degrade that distance.
Yeah. So, what kind of reflection surface do you assume for this sensor?
I thought this is the one where you have the other side was the three mirrors where it was in the back. Oh, no.
No, this is on a flying device.
Okay.
Now, this flying device is having this sensor pointing forward or downwards. So you just look down in a plane like this, which actually goes by 270 degrees, and you project your laser beam down. Now, what do you expect the material reflecting this energy will be? Ground, gravel, anything.
I was thinking that I thought we had lasers that were pretty straight for way beyond 30 meters. They didn't diverge too much, and it's not like you're going through thick fog or something. The medium's pretty good. It doesn't really matter. I don't think it would matter just an extra 100 meters before it hit the gravel or whatever, because you're still hitting that rough surface. Yeah. The point here is actually not so much the medium. For this 30 meters, it is assumed that you have a reasonably low humidity. So it obviously doesn't work in fog. But the actual problem is that the wavelength which is used there, you have easily materials in nature or artificial environments which absorb 95%, 99% of your energy. For example, black leather or felt
is material which is extremely absorbing to that kind of wavelength. There is very little coming back. So if you walk around in the outdoors in your classical stylish leather dress, there's a chance that this thing has severe trouble getting enough energy back. And they needed to rate those kind of sensors to the minimum reflective assumption which you would have in a natural environment. If you would have a mirror on the other side, easy, hundreds of meters, hands down, no question. But unfortunately, you don't have the kangaroos in Australia holding up mirrors just because you want to measure the distance to the ground. And on the other hand, for the same kangaroos, you cannot actually crank up the laser power so much because then you would have a lot of blind kangaroos very soon. That's the trade-off which we have here about. Now, this is a very small device, and those amplifiers are good, but not top-notch. So if you want to go further, you can use that thing here, for example. A SIG laser rangefinder. So the laser rangefinder is not SIG, don't worry. The guy who invented that has actually the last name SIG. So he was German, so he didn't notice that this is actually having this funny association in English. But they're known as the SIG sensor devices everywhere in industry. And this little thing, which looks like a little coffee maker, it's about that size, seriously heavy, 4.5 kilograms. So for airborne, you better have a beefy machine to actually get this thing off the ground. But this thing provides you actually with a range of up to 80 meters. There's much finer optics and much finer amplifiers to do that. With pretty much the same resolution, scanning actually not quite as widely as the previous one, and has pretty much the same frequency resolution. This is the reflectiveness, the energy which is coming back, the maximum range for these different sensors you can get there. And as a reference here, as I said, black leather is a classical testing material for these kind of environments. Black leather has about 2% reflectivity for that wavelength. And this was also in industry a big issue, because where do you find black leather in industry?
Cars you're trying to test?
In the what?
In the cars that you're trying to look at?
No. Think actually heavy industry. On the shoes of the workers which you want to protect. So if you don't measure that these people have actually currently been walking into the safety zone because your laser is not measuring what happens, measuring that shoe, that's a critical issue for that. And they have been testing that quite carefully. As a matter of fact, before this laser became available, this laser rangefinder here became available, it was not allowed to have protection circuitry around safety critical machinery, presses, for example, other devices where you want to have humans far away from. So you need to have safety shutdown procedures for all of these machines. You have heavy manufacturing industrial machines, heavy robots, and you need to guarantee for protection of your workers that whenever the worker is actually stepping into a certain distance to those machines, the machine automatically shuts down. You will find this everywhere. This is mandatory in pretty much all countries. What do you think how these shutdown mechanisms have been implemented or are still implemented in many places? How would you implement that? And you're the newly hired engineer. First job, do something easy. Just protect this machine, make it shut down when your colleague is coming any closer than that area here, or those 2 meters. What do you do?
Like depending on the machine is, you use some disc brakes or do normal things. about to touch it and you have to lock down the machine even if it breaks to save this.
Don't think about how long it takes to power down a machine. If it takes a bit longer, then you make this distance a bit wider. So assume that you have a 2 meter safety distance, and when you get closer than 2 meters, you can still have time to actually shut down this machine before the guy can actually reach into it. But how do you sense that? How do you sense that a person came closer than 2 meters to your machine? Pressure pads on the floor. It's trying to stop over it. So how about somebody's jumping over it? Do you have pressure pads on the floor? I can jump over them. Very large.
Mm-hmm. Do the old spine moving trick and have a laser going all the way around with a sensor?
So that you have these crisscross laser beams and you... No, this is actually was not allowed. Yes. You put it in a cage. That's one way, yeah.
You can detect the heat around your device.
Detect the heat around the device?
I mean, if there's kind of a significant like...
So hopefully you don't have any cold-blooded workers.
But everybody's kind
Yeah.
of heat rate.
So the law in that regard until a few years back was that the only thing you were allowed to use is a mechanical switch. So you need to mechanically trip something. I'm not quite sure whether pressure pads would have qualified as mechanical. But what most companies have done, they just have trip wires and wires around this whole thing. So when you actually run over that, you just break something and you trip it mechanically. It was explicitly forbidden to measure this optically or electromagnetically, for the reason that no company was able to produce enough evidence that this was working under all circumstances, while a mechanical barrier was considered to be more dependable in terms of you cannot trick that thing easily. If there's a mechanical barrier, you have to find a hole through that whole thing, which is easy to protect against.
You just do the same with laser. So have a laser pointing from one point to the other. If someone
Yeah.
breaks it, you just trip it to the shutdown.
Yeah. The point was dependability of those lasers. It was not considered dependent enough that it was safe enough to do that. And this laser changed that because there were extensive tests for will this laser be broken and detected, and you can measure the range exact enough for any kind of material which will be thrown into that one. So this was replacing all of that, and what you do nowadays is you place one of these laser rangefinders just where your machine is. Then you take a measurement of your environment, how it currently looks like, and then you define what is the profile, the frame, which is okay. So anything which is moving or happening outside of this frame is normal traffic, is fine. And everything which is inside your profile, a bit closer to the machine, has to trip the whole thing. For that reason, there's actually also simply a power relay into that whole thing. So you just wire your machine through that thing, and immediately just powers down the main machine if you get any closer to that. And this is now legal. You can actually use that from that. And it's fast and easy. You just plan that once, program the profile which you want to have on the ground around this machine, and this is considered safe enough.
So is it like scanning? Oh.
Yeah, it's a 2D scanning device, which means physically inside that laser, you have inside this blue coffee maker here, you have actually a laser pointing downwards, and then you have a mirror which is on a rotating base, and this is just rotating constantly inside of that one. Hence, it also sounds like a coffee maker. It is sending the laser beam out, taking the same laser beam back, goes into a split prism, for the detect element.
Don't you have the same problem with pressure plates? Can't someone just time it and just dodge it? Like if it will take time to go from one to the other.
Well, I don't know whether you're Spider-Man or something, but that thing measures at 4 times per second. No, it measures faster than that. 4 times per second? 10 times per second? Did I have something in there? At least 4 times a second. So you don't have any chance actually getting closer to that one with normal human running speeds. So it's just simple measures fast enough. That rotating thing is actually rotating pretty fast to do that.
Is the floor being moved around a lot? It seems a lot harder than just running a wire around a reed switch at the end.
Mm-hmm.
Why bother with all these complicated lasers when you can just...
It's a simple. It's also a maintenance thing that this device is a single device where you don't have to check whether somebody moved a pole somewhere on a mechanical barrier or whether your mechanical barrier is still okay. So you still have to constantly look whether all the constants are still there. Fair enough. So sometimes it's you will still say that the mechanical barriers are still easier to be maintained and easier to handle. This is if you have complex formed environments. This makes your life a lot easier. Ta-da. Okay. This is for different forms of range measurement, laser measurements. What other forms of range measurements can we do? We need another example besides time of flight. MTBF. That's a bit of an answer for your question. You know what MTBF means? You know because you're an engineer. Has the computer science gang any imagination what MTBF means?
Wild guess.
Wild guess.
Mean time before failure.
Yeah, mean time between failures. Close. Guaranteed 80,000 hours. That's reasonable. So this is an install and forget kind of installation from that perspective. This can just run continuously without you touching anything beyond that point, which is actually better than what you have with a simple mechanical system, which you just have to maintain more. Okay. This is a bit of the funny end of town. You still recognize those kind of sensors? Have you ever seen those sensors? You're old enough to know them?
I've got some of that.
You got them at home? Well, in what device do you have them at home? You have them as separate modules, or then you're too young. Do you know where they come from? Okay. Those are the ultrasound measurement devices, and they're simple that size little golden plates which are used as transducers, so they're actually pinged, sending out a quite noticeable ultrasound signal. That means the ultrasound signal is so widespread that you actually have also a component which you can hear, and then measures the energy which is coming back from that one. This has been introduced by a company which you usually don't associate with highly sophisticated industrial range finding, namely Polaroid. Polaroid has been introducing those kind of range finders for their cameras, for their instant cameras, which you have probably seen in old movies or from your granddad someplace, where you could take a picture and then can develop a paper photograph directly out of this whole thing, which you can still buy again today. Don't want to make advertisement for whom you can buy them from, but you can still buy them from. And the brand name Polaroid still exists, but only as a brand name. So. Anyway, these devices came from cameras originally, and they're not particularly precise or particularly nice, but that was in the very early phase of people starting to do range measurement with ultrasounds. Nowadays you have ultrasound sensors everywhere, for example in your car. Maybe not all of your student cars have that, but most cars. But this was a bit hard to design back then. I said they're quite terrible. We used them for research purposes plenty, and we wrote to Polaroid whether we could have some of them. Well, we never thought about selling them, but okay. Then a few months back they came with there's a research set, particularly for development purposes, where they sold these sensor elements for about 5 times the price as an Instamatic camera, which has these sensors. So what most research groups on the planet have been doing at the time, they were just buying these cameras by the hundreds, stacking up all these cameras, ripping the sensor out, throwing the camera away, because that was a much cheaper way to get to these sensors back then. And you still see some robots today which have these antique kind of sensors to them. Very nasty limitation of those kind of sensors. They are sensing and transmitting on the same membrane. What does that mean? It's nice that it's all symmetrical, so you don't have this triangulation problem, right? It's all on the same membrane. But as opposed to optical devices, what does that mean for that kind of setup?
The time between successive measurements depending on the range you're sensing.
Yeah. So what you're doing is you're triggering the sensor. Ding. You have to actually stop this membrane at some point, or in this case, you just have to wait until it stops swinging, and then you can start detecting something on the way back, which means it also has a minimum range. If it's too close, the signal is coming back before the speaker has been calming down in the first place, so you have no chance of measuring anything at all, which is a bit problematic. If something is too close, you don't see it anymore. For a range system, that's a bit of a dodgy feature. Okay, but it can get worse. You also have these infrared LEDs on top mounted here, which is simply an intensity measurement system, and you can also see that my camera, which I used to take those pictures here, like every CMOS camera, which doesn't have an extremely strong infrared filter built into that one, is quite sensitive to infrared light. So you don't see any of this with the bare eye. They will never actually be visible for you with a bare eye. But the camera actually was showing them clearly as switched on. It's quite nice. And the middle one is just a sensor which detects the intensity of the light coming back. Extremely short range, and they're basically there to fill in the little gap for the ultrasound sensors, for the extreme close range that you can still notice that somebody is already stepping 10 centimeters in front of your sensor. Okay.
If those are just intensity,
Yeah.
how can that work? You don't know what the material is that you're measuring.
Yeah, not well.
Okay.
Yeah. It's a really rough guess kind of device, and you're perfectly right. If somebody puts a mirror in front of that thing, they will immediately panic because they think it's a few millimeters away. And if you put some cloth in front of it, they will vastly overestimate the distance. Underestimate? Anyway, it's wrong. And the last one I wanted to introduce is those kind of sensors. Very nifty Doppler current profilers, just to widen your mind a little bit what kind of sensors you can get. Those are always a bunch of transducers. They're relatively big, and you have them on any kind of ship or submarine. And you can also plant them simply on the ground of rivers or harbor entries. What they're measuring is the whole profile through the water column. So this is a different kind of measurement than what you have in air, where you're classically only interested in the point of impact of your sensor when it comes back. And the air in between, who cares? The air in between doesn't have much of an impact on that. Now this is different. You can use them without anything on the other side at all. Because if you project energy into the water column, your water column is reflecting energy always. So you send out a signal, and you have a continuous signal coming back from all different levels of distances. And they're all a little bit differently shaped. And they're all a little bit phase shifted differently. What does this tell you?
The currents in water.
The movement of the water in front of you. So with a single sensor device just pointing in one direction, I can measure all the water speeds, not the direction yet, but some part of the water speed, some vector of the water speed, some component of it, throughout the whole column in which you measure that, which is quite impressive to do it with one single sensor. So ultrasound underwater is a quite nifty thing, and you usually combine them with a number of them. So if you have 3 columns pointing into your water column, and you assume that you hit objects in front of you by all 3 of your cones, because they're open enough, then you can actually reconstruct the 3D speed of the object in front of you, which is quite cool. And what this is also used is to constantly monitor current changes in the water column in front of you, particularly if it's pointed upwards or downwards, because it's very important that you understand these shifts in currents if you're in a submarine, or if you're trying to measure something. If you want to lower something into your water column, you're better well informed what the current situation down there is at the moment you point your systems downwards. It's still 160 meters without deafening any whales, so this is not yet at a power level where it would be dangerous for marine environment. You can imagine if you want to crank this up to several kilometers range, then the power which you use for that one could be a bit unpleasant. Blanking zone is only some 20 centimeters to 2 meters with those distances, for the same reason what we said previously with the Polaroid sensors, because you have pretty large membranes here and you measure on the same membrane. So you have to wait until this membrane calms down before you can sensibly measure anything coming back. So why do we do that? I wanted to activate you a little bit to think about how many million possibilities you have if you are put on the spot in you have to build a device which can do this and that in the real world, interact with the real world. There's so many possibilities how to do that, and setting up a good physical experiment is often an important part of your job. What we are doing for another research project at the moment is, for example, finding out how radiation sensitive or insensitive our flight controllers are. How do you measure that? How do you set up an experiment like that? Lay it out? Blast it with radiation. With your pocket radiator. Yeah. Mm-hmm. So you could, of course, just put it in an airplane and fly around for a few months, see what happens, but it's quite low. Fortunately, at the ANU, we have our particle accelerator here at the ANU, which gives us possibilities to just actually have a very controlled beam of protons to actually hit our devices, so we can control it, can measure it nicely. How do you protect it against the wrong parts of your system is being bombarded with protons? still has the same effect as pretty hard gamma rays. And you want to have some parts of your system exposed, but maybe not all of them, because some parts of that need to be used to detect whether a fault has actually happened in the first place. Because putting your flight controller into some experimental environment and just dies doesn't give you a lot of information what actually goes on here. So setting up good experiments, being aware of physical possibilities, being aware of what you can actually sense and how you can sense it, how linear can it be, what resolution can you squeeze out of that one. You will also quickly become quite modest about what is the resolution, what is the precision at which you can measure anything. It is, in almost all cases, a lot less than what you usually expect what you can measure. Classically, if you ask a guy on the street how precise can you measure temperature, I don't know, 5-6 decimals after the comma shouldn't be a big problem. I mean, I have a thermometer with such a display on it. There should be meaning something, right? No. It's actually very hard to do that in any way halfway precise. Okay, I'm not making a physics or electronics course out of this. I cannot. I think I said in the beginning that these kind of setups design the electronics for sensing setups and having an understanding of the physical constraints of some basic sensor devices easily fills two courses by itself.